All right, so I'm making this video to cover some important topics and practice problems for the midterm preparation. This will cover phase diagrams and how to use lever rules, how to identify phases, and how to find compositions, amounts, and how to draw microstructures. So this is taken from the practice exam worked problem 3. I'll recommend you try solving this first yourself and then come back here to see how you could have approached this question and how are different ways to solve similar questions. So, we have been given a phase diagram and we have to identify are the two given points. The 2 points are over here and the other point over here. Let's call them M and N for our reference. This is at 88% silver. So this is a copper silver phase diagram where the x-axis is weight percent copper, meaning that on the left side you have 0 weight percent silver, on the right side you have 100 weight percent silver. So this line that is given to us is, you will see that it's at C naught equals to 80 weight percent silver. That's the initial composition of the sample. And then we have been given two temperatures. For the point M, it's 800 degrees Celsius. For the point N, the sample is at 500 degrees Celsius. For the part A of the question, we have to identify the phases present. And for each phase, we need to find the composition, the amounts present. And then for the part B, we need to draw the microstructure. For part C, we need to find that for the point N, which is at 500 degrees Celsius, what is the percent of pro-eutectic microstructure. Right? So let's try to solve this question point by point. So let's write down point M on this side. And for the part A, we have phases present. So let's start looking at the phase diagram and let's just fill up the different regions of this phase diagram. So the single phase regions have been given to us, which means that this is liquid that is given. This is alpha on the left, beta on the right. Now, in the region over here, you will have alpha plus beta, alpha from the left, and then beta from the right. All right. In the region above this, you will have alpha plus liquid, alpha from the left, liquid from the right. And in this region on the right side, you will have liquid plus beta, liquid from the left, beta from the right. And this is how you can fill up a phase diagram. And then you will notice that you have this point, and at this point you have a transition happening from liquid to alpha plus beta. So at the point CE, you have liquid going to alpha plus beta. And just to remind you, this is a eutectic point. So this is a binary eutectic system, just so that you can recall that as well. So this is the system that is given to us. And to answer the first question of the part A for point M, the phase is present where the M is located will be liquid plus beta. So you have a liquid phase along with a beta solid phase, right? Now the second part of this part A, we have to find the compositions of these phases. And this is where we'll start using the lever rule. So let's zoom in to the diagram. And now we know that it has liquid and beta phase. I'm going to erase this for now. So the C naught, or the initial composition, is given to us, which is 88%. And after this, you can draw a horizontal line. That's how you start working with the lever rule. So let's draw this horizontal line. And let's see where it touches the liquidus line and the solidus line. So on this line would be the liquidus line, and then this would be the solidus line, the beta solidus. And you can see that your tie line, which is this horizontal line, the tie line, touches the liquid part on this point and the solid on this side. Once you get this, you can draw verticals from these points. So let's draw two verticals from each of the points. And then the mark where these verticals touch the x-axis, the composition axis, are the compositions that we need. So because liquid is on the left and then we have beta on the right, the point over here that I'm marking with green will represent the composition liquid, which is this green cross mark, and the one marked with pink, the pink cross mark, will be the composition of beta. So you can approximate this Cl. So let's write that down on this side. So the Cl, the composition liquid, will be about 74 weight percent silver, and then the C beta, so this is the Cl that I wrote as 74 weight percent silver. C beta, which is the one marked on here. Why? Because beta is on the right hand side, so the composition beta will correspond to approximately 92 weight percent silver. All right, this is how you can get the liquid compositions and beta composition. Now similarly, the part 3, in which you have to calculate the amount. Whenever someone says amount of a phase, they are referring to the weight fraction or the weight of that phase. So we can calculate the weight fractions in here. So for easy reference, let us give some notations. Let's call this length as R, and then let's call this length as S. So the tie line and the lever rule, when combined together, say that, let's use this color. They say that you will have this much fractional amount of liquid at the Cl composition in a mix with this much fractional amount of the beta at the C beta composition. So what that means is that the weights or the weight fractions of the liquid and the beta can be represented as, so the weight fraction of liquid will be the one that is opposite to it. So it'll be the S, and for the beta it'll be R. So the weight fraction will be, for liquid, will be written as S over R plus S. And for the weight fraction of beta, you will write R over R plus S. And if you want to write this down in the exact numbers, this will come down to be C beta minus C naught over C beta minus CL. And this will come down to be C naught minus CL over C beta minus Cl. And then just to remind you, we have been given that the C naught is 80 weight percent silver, and you plug in the values. This becomes 92 minus 80 divided by 92 minus 74, and then this becomes 80 minus 74 divided by 92 minus 74. So you solve this, this becomes 12 over 18, and then you can simplify it to be 2 over 3, and then this will simplify to 6 over 18 or 1 over 3. So this will become about 66.6%, and this will be 33.3%. You could write this in percent form, you could write this in fraction form, you could even just write this in decimal. So 0.66, and this will be 0.33, and so on. So this is how you can find the weight of the individual phases, the composition of the individual phases, and what are the phases present. Let's try to do the same thing for point M, and you could even stop at this point, or let's first draw the microstructure at this point. So that would be the part B of this question. So I'm going to erase all these markings for now. So to draw the microstructure at a given concentration and with the phases, given phases, here's what we'll need. We'll need to see what phases are present, first of all. So at this point, we know that the two phases are liquid and beta. And the way the system will grow is that, let's say you started from this point. In this, all you had was just liquid, just like a liquid of this material. When you started cooling it down along this composition line, right at this point, right at that line, you will have beta formation to start. And then when beta forms, it'll form a nucleate. So let's write that down over here. The microstructure, again, we are working at the point M. The microstructure will look something like this. So you'll have this as your these, let's say these some grains of beta. I'm gonna just shade it for clarity. So you have these beta that have grown, and then the rest will just be liquid. So the remainder will be liquid, and the pink stuff is basically beta at this point. And this is your microstructure at the point M, which is 800 degrees Celsius. This is the 800 degrees Celsius line. All right, so this is how you can find the microstructure. Let's try to do the exact same questions for the point N. So you can even stop at this point, so you could try it by yourself, or if you have done that, you could just follow along. So the point N, again, we have to first, for the part A, find what are the phases present. So phases present, and we did that sort of already. Point N is in this region, and we know that in this entire region you will have alpha plus beta. So the phases present at point N will be alpha plus beta. So you have the two solids, alpha solid and beta solid, present in this region. For the second part, to find the compositions, again, let's start using the lever rule. And the first thing that you do to use the lever rule is draw a horizontal line, or the tie line. Let's clean some of this up. And again, we know that the C naught is given as 80 weight% silver. And then when you draw the horizontal line, you have to see where does it touch the respective phases. So you have an alpha phase, which is on the left. You have a beta phase, which is on the right. And you have to see where does your line, the tie line, this is again the tie line, touches the respective phase lines, and it touches at these cross marks. At those cross marks, drop a vertical. When you drop that vertical, you note down that on the left, it touches the x-axis over there, and then this touches it over here. Because we know that alpha is on the left and then beta is on the right, similar to the liquid and beta example, you will have this cross mark as your C alpha, or the composition of alpha, and then you will have this cross mark as your C beta. So again, so for point N, your C alpha, the composition of alpha at point N will be somewhere around, let's call it 3 weight% silver. And I'm just to be clear, I'm writing this point C alpha, so it's somewhere over here. So if I clean this out, you can see how it's approximately 2 to 3 weight% silver. And then for C beta, which is on this right hand side, this one over here, you can see how it's about 98 weight%. So that'll be about 98 weight% silver. All right, let's call this, maybe you can approximate it to be anywhere that is like close to that number. So I don't know, let's call this 97, and let's call this 2. So that's what I've approximated these to be, right? So after this, once you have done, or once you have found the C alpha and C beta, so there's this point C beta, and this point C alpha, then again you can use that RS notation. So what that will correspond to is that you will have this much fractional amount of alpha, because that is on the left, in a mix with this much fractional amount of beta. So let's call this distance as r. Let's call this distance as s. So writing the same what we did for the liquid and beta example, the weight fractions or the amount of each phase, you have the W alpha and then you will have the weight fraction beta. For alpha, because alpha is on the left, you will use the stuff on the right, which is the S. So this will come down to be S over R plus S, and then the beta will come down to be R over R plus S. And then this S can simply be written as C beta minus C naught over C beta minus C alpha. The R can be written as C naught minus C alpha by C beta minus C alpha. What I'm doing is, when I write that, is I'm just trying to find the lengths of my R and S. So you can subtract C beta minus C naught to get the length of S. And then you can subtract C naught minus C alpha to get the length of R. And then you can just add them up, which becomes C beta minus C alpha, which is R plus S. And then you can just put in these values. So this will be approximately 97 minus 80 divided by 97 minus 2. This will be approximately 80 minus 2 divided by 97 minus 2. And then this comes down to be 17 divided by 95. This comes down to be 78 divided by 95. You can leave this in the smallest fraction, or you could solve this for the percent, multiply by 100 and make it a percent. And this is how you can solve this question. Now the part B for this point N is the microstructure. How to find the microstructure at this point. So again, let's go back and look at the diagram. I'm gonna clean some of these markings. So at this point, at the point N, we know that we started from all liquid and then we drew the microstructure at point M. Now, all we are doing is, from that point M, we are cooling our system. So we are just going downwards, all right? So you can imagine this beta that was forming will keep on forming till this line, this line, the eutectoid, the eutectic line, my bad, the eutectic line. This entire is the eutectic temperature or the eutectic line. Till this point, you will have the beta, which is, you could call primary beta, will be forming. And after this, whatever liquid is left will then convert to a lamellar arrangement of alpha and beta. So let's draw the microstructure at point N. You have this circle. You had these pink beta grains. They have grown now, let's say. And then let's say you had a few more grains of beta. So let's draw one more over here. And then you will have alpha and beta. So all the remainder liquid has now converted to alpha and beta. To draw that out, let's draw some horizontal lines. And then you can draw it in different orientations. And then I'll draw one in this direction. And then you can keep drawing them here. And then what I'll do here is I'll color the alternate to show the distinction between alpha and beta. Because again, remember, this is a lamellar arrangement, an alternating arrangement of alpha and beta. So you can sort of color the alternating systems just to clearly demarcate the difference between the alpha and beta. So The yellows that you have here, this is your alpha. And then the green shaded, you could call them as beta. And this combined makes alpha plus beta, eutectoid. Eutectoid. My bad, this is a eutectic system. Eutectic microstructure. And then the pink one just remains as the pro-eutectoid or primary beta. Right, so these are